conversation, for example, and it's trying to detect words. Right? It's trying to understand. That's what NLP is all about in artificial intelligence. NLP, natural language processing. Right? So you could use the techniques, the methodology, the terminology, and the actual technical terms used in this topic of finite automata, and you could use that to in speech processing, right? Or optical character recognition, or just what the AI guys, artificial intelligence, just call vision, right? So recognizing objects in some two-dimensional, three-dimensional image. Okay. Now, in passing, well, the textbook mentions just briefly the concept of Markov chains. I don't know how many of you know what they are. I'll just briefly give you a quick overview because it's mentioned in the text. Now, these, it's implicit, it hasn't been spelled out, but this state transition table, all this, this table of state transition rules, in other words, if the current state is such and such, in comes input signal that is such and such, then the next state will be such and such. Right? Now, the decision as to what the next state will be, given the current state and an input signal, that decision here is deterministic. Right? There's no doubt. Given the input state and the input signal, the current state and the input signal, then the next state is determined without any doubt. With 100% probability, it's determined. Now, if you become more flexible, and so then there's only a probability that a given next state happens. There might be maybe a smaller probability that some other state becomes the next state. Well, all the mathematics of that, that's what Markov chains is all about, because now you're talking about probabilities of transitioning from this state to that state, right? And you might have probabilities of transitioning to several states, and then you have to add up all those probabilities to get one, because you have to transition to one state. You might stay in the same state, but it's still a next state. So all those probabilities of transitioning to some other state have to add up to one. And so there's a whole mathematics of this. It's called Markov, a Russian guy, I guess, who invented this stuff. Markov chains. Yeah. And why chain? Well, because you got to you're transitioning from one state to the next, to the next, to the next. And you get a whole chain of states. Okay, with Markov chains. And it's maybe senior level, I guess, in a math course if you did Markov chains. You can prove some interesting theorems with it. Anyway, so finite state automata, in other words, deterministic transitions from one state to another, and then the probabilistic equivalent, similar, but you're not transitioning then with certainty, you're transitioning with less than certainty, with a certain probability. But those two can get used for these applications, like speech processing, like Markov, something called HMM, hidden Markov models. That for a while, several decades, that was really big in speech processing. Favorite technique. Okay. All right. Now, okay, so that sort of ends the overview of what a finite automaton is, and now we start getting into the more detailed description of what a finite automaton or finite automata, the plural form, are. Okay, and we'll take an increasingly mathematical perspective. We'll take these definitions and we will write them in mathematical terms. The definition of a finite automaton or finite automata
will be written in mathematical terms as part of the definition. Okay, so we'll give what will now follow in the next few sessions will be a precise definition of what a finite automaton is, an FA. Okay, so we'll give an actual definition of what it is. We'll introduce terms to describe what an FA is and how to manipulate, how to change states and whatnot in a finite automaton. Okay, so definition, terminology, and then later, quite a bit later, then we'll start getting theoretical results. Once we have these two under our belt and get a feel for what can be done, then we can start getting theoretical results. And well, this is more into like the middle of part 2, in a sense, of the text. So it's sort of later chapters. So it's sort of getting a fair way into this course. But using finite automata, we can get a feel then for their power. What can they do? But also the limitations. What can they not do? Which is fascinating. I mean, there are some mathematical proofs showing that certain types of computations or questions, if you like, have no answer. Cannot be computed. Right? Their computability is nil. Cannot be computed. Impossible, and provably impossible. And it's it's fascinating stuff. I've said it several times before, but we will do that in part 2 of this course. The finite automata definitely have limitations, theoretical limitations. There are some things that no computer will ever be able to compute. Well, unless we totally radically change our conception of what it is to compute. But okay, all right. So there's a sort of a summary of what is coming. So we're getting into the theory now, the full mathematical theory of what finite automaton is, or what finite automata are. Okay. So will give us a feel for what they are, what they can and cannot do, their power and their limitations, and just by playing with, for example, state diagrams, in other words, state transition diagrams, state transition tables, stuff like that, and with the definition, the definition of finite automata and various proofs, using these. So we'll do all this stuff, but in a fairly simple context, a fairly simple setting, to give you a feel for, well, at least the first two. This will come a bit later, right? So you'll get familiar with the use and the nature of, and the power of, and the limits of finite automata. So that's what will come in the next couple of sessions. And in fact, well, jumping ahead a little bit, in the next session I will give you'll see a fairly simple state diagram. So it'll have various states. Now it's a little bit more complicated than the very simple one that we used for the ADC, automatic door controller. It only had 2 states. Well, in this one, the next one, our second example of a finite automaton has 3 states. Right? So next step up. But there'll be new terminology introduced. There'll be some new things, and then we'll start analysing this state diagram, and that will then sort of become a model for future use throughout the text. So the next few sessions, in a sense, are the absolute bedrock, the foundation for the theory and the theorems of pretty well the rest of the text. So, basic. So, hope you enjoy it. Ciao.